This is Dr. Wood with Citadel Civil Engineering. This is CIVL203 Dynamics, Learning Objective 4.2, in which we're going to discuss rigid body fixed axis rotation. This represents another major concept that we're adding to our arsenal. Once we have this concept, we'll be able to do pretty much everything we need to do talking about general plane motion, just working with superposition. And so this lecture is a little longer because we need to cover some pretty important new material. So as a reminder, this is in chapter 15 of your textbook where we're looking at rigid body kinematics. Here's an example of some fixed axis rotation. So first off, we need to define our terms. When we say fixed axis, what we mean is that in 2D, we have one fixed point. That's in 2D. And then everything rotates around it. So that is the center of rotation. So if we take a look at these windmills from this wind farm, reminds me of my home back in West Texas. Where's the fixed axis? Well, it's the center of the windmill blades, right? So there's this one point in the middle that's not moving. And so that point is the axis. Now, when we're looking at 2D, we might have a disc like this, and the axis of rotation is actually pointing out of the board. So 2D simplifies it in that a point is all we need to define the K direction that is our axis. So that point is the center of our rotation. Now, when we talk about rotation, we're discussing the variation in theta. So that's going to be theta, theta dot, and theta double dot. So immediately your mind should have a little, maybe a subtle groan that now we're talking about polar, right? And polar coordinates were not our favorite. But that said, this isn't actually all that bad. We're going to make some simplifications. The first thing we're going to start with when we think about rotation is theta. And we're going to call that the angular position. Angular position. Theta dot, that first derivative of theta with respect to time, we're going to give a new symbol. It's an omega, so it looks like a W with kind of curly tops, right? Omega. That's going to be our angular velocity. And theta double dot, or the second derivative of the angular position with respect to time, we're going to use the symbol alpha. Alpha looks like the little fish thing. And that's going to be our angular acceleration. Angular acceleration. So we have this theta, omega, and alpha as we think our way through this. So this is our variations in rotation. Now the thing that is so cool about this is that you see how we have this word in front of position, velocity, and acceleration? We already have a whole lot of rectilinear equations set up to help us handle acceleration. And it turns out that those equations are completely corollary if we think about them in terms of angular acceleration, angular velocity, and angular position. So any equation that we have, an S, a V, and an A, we could just replace theta, omega, and alpha, and those equations will now work for angular kinematics. And so that's a pretty powerful tool. It doesn't take a lot for us to just kind of say, boop, swap out some symbols, and now we get to work it. There'll be new context that we have to think through, but this occurs all over the place. So this is our rectilinear kinematics. Rectilinear kinematic equations, they just apply to our rotation kinematic terms. We can just hot swap those symbols and we'll be in business. So that's something you'll want to do, and they're all over your FE reference handbook, 78, 79, 81, 82. So that part's not too bad. But remember, when we're doing rigid body kinematics, we want to keep track of everything. And so, for example, we might think about happiest place on earth, the carousel at Disney World, right? And so hopefully everybody's had an experience on a carousel or they know something about a carousel, but you're riding these horses in a circle. And so we might look at a plan view of a carousel. Hey, look, there's a plan view of a carousel. And here you are out here, you're riding your horse, you're having a great time, right? So there you are. Now, I'm going to go ahead and shut down the PowerPoint because we don't need it, so that you can see this full size. So there you are on the carousel, and we're going to use this carousel to help us think through how we keep track of your kinematic properties, knowing that you're on a fixed axis rotating body, like the carousel. And so the first thing that we're going to want to do is we're going to want to keep track of your position. Now remember over here we're using theta, theta dot, and theta double dot, but we've redressed them as theta, omega, and alpha. And so what we're going to end up using is polar coordinates. So I'm actually going to sketch these out here a little bit different. Okay, so out here I'm going to have my radial unit vector and my transverse unit vector like that for my polar coordinates. And my position vector to where I am, or where you are, is right there. Now I might have some, reference line that's going on here, and this would be the angle theta. And so if we want to talk about this position, that's just going to be equal to the distance, the radius, in the radial direction like that. Now remember that that radius isn't changing. If you're sitting at one place on the carousel and the carousel is a rigid body, you're never going to be farther away than you are currently from the center or the fixed rotation point. And so this is pretty easy. Now, the other thing we might want to know is kind of how far we've moved. And so this would be our delta S, or we'll just call it S, our position. Remember our scalar position along the path, right? And if we remember from geometry, S is just equal to R times theta, where theta is in radians. And so this is another equation. It's actually not in your FE reference handbook, but I'd highly encourage you to add it because this is going to be the important piece, or an important piece, thinking through position. And so I would say at this point, this is pretty easy. This is your FE reference handbook 78 position. All right, so we're feeling good. Now the next thing we want to talk about is velocity. And when we think about velocity, what we're going to do is we're going to pay attention to this. So which direction are we headed? Well, we're headed tangential to our path, and our path is along a curve. So we can use our path coordinate system to say, okay, yeah, I know what's going on here. My velocity is pointing this way, right? This is why you sit on the horse facing forward, is because that's the direction you're moving, your velocity. Now that velocity is rotating as time goes on, but it's a thing. The other thing we'll see is that this body is rotating around its center with an angular velocity of omega. And so let's think through how these two are going to interact. If we go and look at our polar equation for velocity, we say that velocity is equal to r dot in the radial direction plus r theta dot in the transverse direction. Okay, and that's probably not one you memorized, but that's okay. Now, we're going to change some things. So first off, if r is constant because we're on a rigid body, what happens to r dot? Well, when we take the derivative of a constant with respect to time, it ends up going to 0. And so this whole term is going to drop out. We'll notice that that matches our picture up here. There's no part of the velocity that's pointed in the radial direction because you're neither moving away from or toward the center. It's at a constant radius. We've also got a new name for theta dot. That's going to become omega. And so our velocity is always going to be equal to r times omega in the transverse direction, or in the more general sense, it's a cross product, omega cross r. Okay, and so if we look at this, omega is coming out of the board. It's counterclockwise positive. And so if I do my cross product right hand rule, my right hand comes out of the board, that's omega. and then I curl my fingers in the direction of r, so they're going to go that way, and I find my velocity is perpendicular to r there, omega cross r. So that's a cross product. So this truth, super handy. Typically what we'll end up doing is using the cross product, just the right-hand rule to do r times omega in the transverse direction, but sometimes it's helpful to actually do a full matrix cross product for the velocity. And so this is our velocity equation. So if polar looks terrifying, I think the velocity for fixed axis rotation is a little less scary. And this is in your FE reference handbook on page 78, and it's discussed in Beer-Johnson 15.1b. So remember, this is due to the radius being constant. So we have position, we have velocity, and now we want to go after acceleration. So again, we're thinking about your acceleration as you ride your around the carousel. You know that you're looking forward in the direction of your velocity in the transverse direction. You're on a rigid body, so nothing's changing that direction. Acceleration, we're going to do the same sort of thing. So let's start with our polar equation for acceleration. The acceleration from polar equation, I'm going to have to copy this from my notes because I don't memorize it. R double dot minus R theta dot squared in the radial direction plus R theta double dot plus 2 R dot theta dot in the transverse direction. All right, let's do the same sort of thinking here. R double dot, well, that's going to go to 0, right? As we take the second derivative of a constant, it's still going to be 0. R dot's okay, theta dot's going to become an omega. R is okay, theta double dot's going to become an alpha, and then R dot is also 0. So if I'm going to put the transverse part first, what we'll end up with is something like this. We'll have alpha times R in the transverse direction minus R omega squared in the radial direction. So this term goes here, and this term goes here. Let's take a look at what that would look like over here on our diagram, on our kinematic property diagram. In the transverse direction, we're going to have this alpha R component, where alpha is the angular acceleration. So in this case, we're showing it as an increase in the angular velocity, and the radius is how far away we are. Now we'll notice those relationships are the same as they were for the transverse component of the velocity, and so it turns out that that is also going to be alpha cross R. So this is the same sort of thing. Now I'm not doing a proof, I'm trying to build those mental models for you, right? The proof's in your textbook. Now, that's all fine and dandy. And then when we think about the radial component, we'll notice, well, it means that you're experiencing what we formerly would have called a normal acceleration equal to omega squared R. And where that actually comes from is that this is a triple cross product. So this would be omega cross R. That's how we would write that. Now, the cool thing about a triple cross product like this, where we have the omega twice, so we're going to do omega cross R, we're going to get the velocity, right? That's the part inside. And then we're going to do omega velocity, and it points in the opposite from the radial direction. So the other way that we can write this is to say that we're going to have alpha cross R minus omega squared R. So R points out, we have a negative because omega squared R is going to point back toward the center. And this is our acceleration equation. This is the one we'd want to hold on to. And again, it's in your FE reference handbook. It's in your FE reference handbook on page 78. So this is pretty cool. Now, if we look at our diagram here, we'll notice that this component here, this is our transverse, or our tangential component, and this is our radial or our normal component. So when we think about this transverse or tangential component, that should put us in mind of our path coordinate systems. Now, we didn't really have a transverse or tangential component. We did. It was just the rectilinear change in the velocity. Now that's alpha cross r. But in the normal direction, we had that v squared over rho. And so what I want to show you real quick is that that's actually the same thing. So we said the normal direction was equal to v squared over rho. Well, rho is now our radius of curvature. Well, what is v squared? Well, the velocity squared is just going to be r squared omega squared, or omega squared r squared, either way. Right? Order doesn't matter. And so if I substitute in our new equation for velocity into our path equation for acceleration, I'm going to get this. Well, if I look at that, one of my r's will cancel, and I'm left with omega squared r. So the difference here is that when we were looking at particle kinematics along the path, we were looking at the velocity of the particle itself and thinking about how tight the radius of curvature was. And that was what would give us that normal acceleration required to turn the velocity. Now we're looking at an object on a rigid body, and that normal acceleration to keep it on the rigid body is associated with omega squared r. So the r component's not going to ever change the way it did in the particle. What will change instead is that it will spin faster or slower, a larger or smaller omega angular velocity. So this is our kinematic equations for fixed axis rotation. Just remember what the arc length is. Velocity is equal to omega cross r, and the acceleration has a transverse or a tangential component, alpha cross r, and a radial or normal component, negative omega squared r. And so with that in mind, we'll work some problems together, and I'll see you in class.